In the next few classes, we will be talking about mixtures, which is not just pure water, for example, but or one phase of pure water, but when two phases are present together or multiple components are present together, how to characterize really such
Where does the
system
syllabus end? Or is it just like
I don't know. You're talking like an undergrad. It's a PhD class. Life is your syllabus.
because I
Something
opened
like
the
that.
notes yesterday and it just doesn't seem to stop. So I was like,
Yeah, I don't know. We are having a great time. You're still here. I'm still here. Most professors complain that students don't show up to class. I mean, I already told you all that I will give you 10 participation points. Almost. Why are you here if you're not enjoying? So I don't know. I specified at some point that it's qualitative, and secondly, the last part will cover almost half of the semester, right? It's the fourth item. So that's what we are doing. So, okay, let's get back to mixtures. So we are talking about how two phases or two components stay together, right? And we saw an example of this last time when we characterized a phase boundary, and we said that when you have a pressure temperature part and you have some phase boundary where this is some phase, let's say this is liquid and let's say this is vapor, and we characterize the slope at any given point as dP by dt is equal to delta S by delta V. This was our Clapeyron equation. And we had an approximation to this Clausius-Clapeyron equation where you assume that delta V, the one side is the ideal gas. So when we did the Clausius-Clapeyron equation, we specifically did it for which one? We did, so this was Clausius, and this is exact, okay? Clausius is exact. And from this, we did Clausius-Clapeyron, which looked d ln p by dt is equal to delta vaporization h by RT squared. So we did Clausian-Clapeyron, which is only for ideal gas, and we assumed a few things. And we did it only for liquid going to vapor. In literature, and I think one of you asked me, why is this used for proteins? Why do we ever care about proteins getting vaporized? It kind of sounds funky. People use this even for solid to liquid. People use it even for melting of a protein by assuming that the melted protein is an ideal gas. It's a really bad assumption, but if you go and look up literature, you will see countless papers using Clausius-Clapeyron equation in biochemistry and elsewhere. You can apply this to any phase if you're just willing to assume that the other phase, liquid, is an ideal gas. So it's an assumption, but you state what you have.
But if you're making predictions assuming ideality, that doesn't necessarily how accurate
it still works quite well. That's the thing about thermodynamics. The deviations are there, but even ideal behavior captures a lot of the physics. It's, I mean, think about heat capacity. Ideal gas says that heat capacity is 3R, 3 times gas constant. Most things deviate from it, but at room temperature and everything, the deviation is not that far. You have to go to like 200 Kelvin to start seeing deviation. So ideal gas approximation is so simple, yet it works actually quite well. So this was just a recap of, the Clausius equation last time and Clausius-Clapeyron equation, which is, so the thing to remember is Clausius equation is exact. Clausius-Clapeyron equation is inexact. It's an approximation. And Clausius equation is very easy to remember if you look at this form. As long as you remember dg is equal to v dp minus s dt, all you have done here is to equate this to 0, right? And then you get Clausius equation. So if you remember the fundamental equation for G, which you should, it's super easy. So before we start to talk more about mixtures, I want you all to be a little bit more engaged today. And there are two equations that we are going to use, or two concepts. And I'm going to be stuck. I know the answer, but I want one of you to help me. Okay? So the two questions today are questions for today that will help us move forward. And we want to characterize this critical point, and we want to talk more about mixtures. But in order to do all that, there are two questions. First is, I want someone to help me derive this equation. For ideal one component system, mu, chemical potential, is equal to mu naught plus RT ln P by P naught. And who wants to help me with this? How do we get this equation? They've all seen it.
Did we do it for free energy?
So tell me step by step. So let me draw Omar. That's Omar. So tell me, Omar, how do I start? You can come and write here if you prefer. You want to do that? Come. Come. I don't have a high chair for you, so you have to stand. So Omar's proof.
I don't quite remember, but
Oh, you should. You volunteered. Let's start.
Yeah, I don't know, probably from dg
Very good. Is equal to?
is equal to VdP
Mhm,
minus SDT.
mhm,
Yes, right?
mhm.
And that's about it.
Okay, let's look at partial G.
So you mean this?
Partial G by partial P at constant T.
Well, that's V.
Okay,
Right.
let's write that down.
Yeah.
Okay, does that give you an idea how we proceed from here? Okay, you did enough. Anyone else
Yeah.
wants to help me? How do we move from here? What we want to derive is mu is equal to mu naught plus RT ln P by P naught. This relation is so important. And when I did it, everyone nodded their head. Oh, yeah, obvious. And like all of you are like, wait, what? How do we get this? This is what happens in thermal. So how do we go from here?
Should we add dn or to dg formula?
I will do whatever you want me to do.
I agree.
We are talking about a single component system. One more. Yeah. So what do? I assume my ideal gas says this is equal to RT by P, right? Then I can integrate it. Then I will say dG by RT is equal to dP by P. So at constant temperature. So the reason, Alex, we don't have mu dn here because I'm talking about single component ideal gas. Okay. So G naught to G, P naught to P. Okay. Or G minus G naught is equal to RT ln P by P naught. Or G is equal to G naught plus RT ln P by P naught. Okay, that's fine, but we are not quite there. The equation I wrote has mu. How did you get that one? Now, Alex, you can help me.
Well, g is mu n.
G is mu n, right? For anything, for any mixture, G is equal to summation mu I ni, right? And if it's a single component system, ideal or not, mu is just G divided by n, okay? Now you'll be, oh, where did the n come from? Well, if you had to be really cautious, the n came from here. Okay, that's where it comes from. So you divide by n. Let's call this 1. 1 plus 2 gives mu is equal to mu naught plus RT ln P by P naught. And most of the time, people set it's usual to set P naught is equal to 1 unit, 1 bar, 1 atmosphere, whatever unit you are. If you set it is equal to 1 unit, then it looks mu is equal to mu naught plus RT ln P. And this is what led to the discussion of fugacity, right? And fugacity, we said, well, most things won't follow this behavior, but we still want to introduce F as the thing that follows this behavior, right? And then we talk about fugacity coefficient. So this was the first thing. And we will get back to this when we really talk about free energy of mixing of mixture. So keep this in mind. In your homework 5th problem, you're deriving this same relation. You're not doing it from mu, but this is so important. I will come back to it even later. The other thing I want you to help, so I said I want you to help me with two things, and you all kind of helped me with the first one. Let's see if you can help me with the second one. I want to think about the van der Waals equation of state, which is P is equal to nRT by V minus NB minus AN square by V square. And I want you to plot this for me at a fixed T that is known as an isotherm, right? So I want someone to help me plot this thing. Pressure versus volume at a fixed T. Why are we doing this? So today's class, if I go, there are two topics today. It's a highly nonlinear manner. It's like one of those movies, right? Everything is complicated. So today we are really going to talk about critical point, where it comes from, what is the understanding behind this, and then that is sort of a mixture, how liquid and volume, liquid and vapor stay together, and then we will start talking about free energy of mixing. Okay, and when we do free energy of mixing, that's when we will use this mu is equal to mu naught plus RT ln E relation. For now, let's focus on the critical point. In order to do that, I want someone to help me plot this. Where is Vanessa? What do you think, Vanessa? How will this look like? At a constant P, and constant V, and constant A, and constant N, right? So you can think of P as Y and V as X, right? So what is the order of this equation? Is it a linear, quadratic, cubic, quartic? P as a function of V, what is the order? But let's say all of them are contributing. Why do you think the first will be strongest? That's an interesting point.
Oh, just because the second one is over B squared, that's a smaller.
So you're correct. So the first term will be strongest at very high temperature, right? Because it's T over there. If I reduce the temperature, so you can already see why this answer is complicated. If I reduce the temperature, then the second term will also start to matter. If I increase the temperature to infinity Kelvin, then the second term will not matter. So I want you to think about when both of them matter. Then what is the order in V? Is it a cubic? Because when I multiply these two things together, and if you write it down, the fractions are confusing. So this is going to be PV minus NB multiplied by V square is equal to nRT V square minus AN square V minus NB. So that's a cubic, right? The highest term in V is cubic. So what does that mean? For a given value of pressure, how many volumes should we have in general? If it's a cubic, 3. Okay. But as the temperature becomes very high, then what Vanessa said starts to apply. So at low temperature, this is true. At high temperature, we get primarily P is equal to nRT by V minus NB, or P multiplied by V minus NB is equal to nRT. Approximately. How many solutions will this have? 1. Does anyone know how to plot this? It has a name from coordinate geometry. Yeah, there you go. He took his coordinate geometry seriously in India, like me. It's a hyperbola. Do you know how to plot a hyperbola? It's like this. At very high temperature. As you can see that, right? As V goes to 0, P goes to infinity, right? And as V goes to infinity, P goes to 0. V goes to 0, P goes to infinity. V goes to infinity, P goes to 0. And only so at very high temperature, this is going to be true. At low temperatures, however, there will be 3 solutions. And if you went and plot this in Mathematica or MATLAB or whatever, by assuming some values for A and B, you will find that the solutions look as follows. The curve looks as follows. at low T. So this is what I meant. So at any particular value of P, you have solution number 1, you have solution number 2, and you have solution number 3. Okay, let's give these names. I want to call this point over here. So I want to study first this low temperature or medium. Yeah, go ahead.
We're not really going to zero volume, right?
No. Okay. They are in thermodynamic limits. So zero volume means lower volume.
Because it looks like the graph is correct.
Yeah, it's thermodynamic limit. So that's the thing in thermodynamics. Volume becomes smaller. It can never go to zero. We are always in the limit. It's kind of contradictory, right? We are always talking about infinite volume while we're still decreasing it. Yeah. So this point I want to call L, something up here. This point I want to call D. This point I want to call B, C. Do I want to call that? Okay, there's a reason why I'm calling that one as L and this over here as G. Okay, you will see L stands for liquid and G stands for gas. And in the middle, I will call this one as A, this one as B, this in the bottom as C, and this as D. So why did I call it a G? Even for a van der Waals gas, as you keep increasing the volume more and more and more, a van der Waals gas will start to approach an ideal gas, right? If there are 10 of you in a room interacting as per van der Waals, and I put 10 of you in a football field, then you would be interacting as an ideal gas, right? We barely see each other. And ideal gas is a gas, it's not a liquid. So as you go to this part of the curve over here, you approach the gas phase, okay? You become purely gas. As you go to very low volumes, you start to see some condensation in the van der Waals equation of state. And you already saw with the heat capacity that van der Waals is funky, right? It gives a mode in the heat capacity and things like that. So as, yeah.
At very high volume, the two graphs converge to the same.
Which two graphs?
The two at high temperature.
I'm making no such claims. They might not, no claim. You can check.
How are you like guaranteeing that you'll have at least one real solution to your qubit, but you could potentially have like imaginary solutions as well.
Yeah, good point.
You're assuming that you'll always have an existence of 3 critical points, but mathematically that need not be the case because you're looking at different pressures and volumes.
Yeah, it's possible that you reach a regime where I think that converges. That is what happens at higher temperature. So even at higher temperature, you do have two complex solutions. It is still a cubic at high temperature. Vanessa said us ignore the second term, but you really believe Vanessa?
I won't comment.
You won't comment. Very political answer. Even at high temperature, there are 3 solutions, but 2 of them are actually complex. That's exactly what happens. And they are complex valued and they're complex conjugates of each other.
But at lower temperatures, it's where you're looking at these 3 things.
Lower temperature, I think you can prove quite rigorously. I'm not going to do it. That it will be 3 real valued solutions. You have to look at whatever the matrix is called and stuff. You can prove it for this equation. Now you could find some funky values of A and B where it doesn't happen, right? That's possible.
At low volumes and high pressure, there exists only one solution because there is only one value.
Sure, as the curve shows, yeah.
Even at a very high.
Yeah. Go ahead.
Does the local maximum between forest and B have any physical?
Yeah, so let me get to that. What does this minima and what does this maxima mean? So this van der Waals equation of state, basically the physical picture here is, once you start from here, you have a gas. Now imagine you are compressing it, right? As you are compressing it, if you compress it too much, you will end up with a liquid. What we want to understand is what happens in the middle. So it turns out this van der Waals equation of state actually gets this. Van der Waals equation of state is also an approximation, right? If you really want to use it for reality, it's an approximation. It assumes things are hard spheres with some attractive forces, right? So it turns out that this point D and this point A have physical significance. B and C and everything in the middle is kind of spurious. Okay, so what do I mean by that? So this is van der Waals, and if you were to plot an isotherm for a real liquid, you will find that it actually looks something like this. It goes like this, then it becomes almost a flat line, and then it starts to go down. Okay, so all the features that you're getting in the middle of the van der Waals don't really matter that much generally. It's an artifact of our approximation of our model, but it's still quite powerful, right? Ideal gas gave nothing. So what do I mean here? So this over here still corresponds to the G point. And this corresponds to the L point. And what I drew here is for not an ideal gas, opposite of ideal gas. This is a real substance, not an ideal substance. So what are we seeing now? You start at very high volume. It is almost gas, it's almost ideal gas, and you start compressing it. When you start compressing a gas, has anyone compressed a gas before in their houses? When?
I had commercial project, failed commercial project. We
Okay.
had to use two engines,
Yeah.
one in reverse to make a compressor and pump.
Yeah, I was worried someone would say they held a fart or something like that. But an AC does that, right? AC has a compressor, a fridge has a compressor, we use it all the time. So when you compress a gas and you compress it too much, it becomes a liquid, right? And you can see this even from, so let me draw this diagram on the next page. You have pressure, you have volume, and you have something like this. And this is gas, this is liquid. So this is an isotherm for a real substance. This turns to be quite true. This is the behavior that is normally seen. For a real single component system, multi-component things can be complicated, but still this is quite powerful. So we start at gas, we compress it, you start seeing liquid. This region over here corresponds to the coexistence of liquid and gas. Okay, both of them coexist. And if you think about the phase diagram of water, you will see why this makes sense. In the phase diagram of water, in pressure, temperature, we had solid, liquid, gas, right? So we are talking about isotherm, which means a vertical line, right? Constant vertical line. So, and decreasing volume is the same as increasing pressure, right? So increase the pressure along this one. You start from a gas, you cross this boundary, and then it becomes a liquid. But in the water phase diagram, we had a PT coordinate. So the liquid vapor part appeared as a single point, right? At a fixed temperature. At a fixed temperature, PT diagram shows liquid plus gas coexistence as a single point. But that's kind of misleading. If you go to a pressure volume diagram, you realize that actually a lot is going on. This is a PT diagram, right? So it cannot tell you about the change in the volume of the system. So at this point over here, where you're seeing coexistent, it actually corresponds to this full region, right? And this yeah, one moment. This should be nostalgic of what you did in the Carnot cycle, right? When you expressed it in different spaces, right? Different spaces will have different stretched out projections. Yeah, go ahead.
So I still don't understand how are the two curves in the previous page different?
Which two curves?
The first one and the second, last one.
Which page? This page.
Yeah. So
This top curve and bottom curve.
yeah,
Top curve is van der Waals. Bottom is a real material. So the real material follows van der Waals from L to D and from A to G. Everything in between from D to A is an artifact of the van der Waals equation.
Okay, it's an artifact.
Yeah, this is an artifact because van der Waals says they're cubic, it fails over there, okay? Now, what would an equation of state look like for a real substance that gives you a pressure volume curve? This could be a homework problem later. So, but this should be very clear. Here I'm making no assumptions at all. In the pressure temperature phase diagram, you stay at a constant temperature and you keep increasing your pressure. You keep increasing your pressure. You get to the liquid gas boundary, and then it as if automatically you become all liquid. But that's not really true if you're thinking in the volume space, right? In the volume space, you can keep compressing, you can keep compressing, you can keep compressing, and you will see that there's a liquid plus gas region. Here, how much gas do we have? 100% gas, right? And by the time you get to this point, it's 100% liquid. Later, when we get to phase diagrams, more in detail, we will talk about Lever rule and other things which will allow us to calculate how much gas is there, how much liquid is there. Okay. So what this part is, it's really coexistence. Coexistence of liquid and gas. They exist together. Great. So with this insight, now let's go back to our van der Waals picture of the equation of state, and let's try to draw it as the temperature goes from low to high. Let's draw a set of curves. Okay, I will draw it van der Waals, and I will always tell you where it is making an approximation. So I'm telling you the correction as how it looks like. So we have our pressure and volume. At low temperature, it's going to look like this. When the reality is that, yeah, I mean, and you know that in reality, actually, there is a straight line connecting this point to this point, but you know, I'm going to ignore that for now. As you increase the temperature, as you go to very high temperature, you know, it's going to look like this. So what happens in the middle? So this is low T, this is high T. Okay. And maybe I should have brought like a Python notebook for this to show you, and you can go and plot it yourself and change the values and see that as you increase the temperature, this curve lifts up and it starts to look like this. So this gap that you're seeing between the bottom and this point, it becomes smaller and smaller. As you lift it further, so this is as the temperature increases, T increases. As you lift it further, so what's really going on? This part in the middle corresponded to our two-phase region, right? It's becoming smaller and smaller. So this was liquid plus gas. This is also liquid plus gas. This is also liquid plus gas. You can almost join these things and you can see like there is a boundary. There is a dome starting to appear, right? This left side of this is liquid. The right side of this is gas. And the middle region is liquid plus gas, right? And the dome becomes tighter and tighter and tighter until you reach a curve where the liquid plus gas, even in pressure volume space, is 1 point. And then when you make the temperature very high, all of this is liquid plus gas. You can interconnect. Physically, what happens here is that the surface tension between the liquid and gas goes to 0. And it's very easy to form as much gas as you want, as much liquid as you want. It just goes crazy. That's the critical point. So this point over here, the value of pressure, PC, and the value of temperature, volume, VC, and the temperature at which it happened, right? Because this thing itself will correspond to some isotherm, right? That isotherm, T is equal to TC. So together, PC, VC, TC characterize the critical point. It is when the surface tension, so there is no cost to create just lots of liquid in between gas, but there is also no cost to create lots of gas in between liquid. So it just like goes back and forth. In StatMech in 687, we will study a little bit more about this. There are things known as critical opalescence and stuff like that. You can go and look up videos on YouTube. So the surface tension between liquid and gas disappears. And both have same density. So van der Waals gas actually shows a critical temperature. Ideal gas does not show critical. Correct?
Yeah, so, how do you decide the liquid and gas? From what you told in the last,
From here.
from here. So,
The liquid and gas region is between here and here. This is coexistence. This is coexistence.
So
of-
it's just below the maximum.
Yeah.
So below the maximum.
It is strictly speaking between the two inflection points. Yeah, you're right. I could mathematically characterize this better, but it's strictly speaking, it's where yeah. I'm not doing that because I don't want to get too much into that. But what I do want to do mathematically now is to think about how would you calculate PC, VC, and TC from the equation of state. What I have drawn over here, the physics that I described to you, that the dome becomes tighter and tighter. Mathematically, can anyone help me write it down? You want to help me write it down mathematically, or do you have a question? Go ahead.
Could you just maybe give us like 2 seconds? to cut this?
Sure.
I'm trying to catch up.
The notes are online. You don't have to copy everything. But I will wait.
How do they determine this experimentally? Like the liquid gas coexistence, how do you see the difference between that and experiment? And this make the surface tension measurement critical?
Critical opalescence, you should go and look up. There are lots and lots of. They just keep making isotherms, and there are lots of. I will post some links online. People have been working on it for like 200 years. I mean, this is something they started looking at quite early on. So yeah,
So wait, Kinjal's question was about that dome and where its endpoint should be.
yeah. Kinjal's question is, what is the mathematical characterization of this thing? Why do I know that liquid starts for, if I did not know about the real one, if I knew only about this one, how did I know that liquid starts at this point? Kinjal's question is, why doesn't the liquid start at this point, right? That's what his question was. And the answer, since you insist, this point has something special. Notice the slope there, what's going on? It's an inflection point. So B is an inflection point. So you find the inflection point and then find the brother of the inflection point on the left side, and we join them. This will become clear when we do common tangent rule in a little bit. So B is an inflection point, which kind of gives you the answer to what I had just asked over here. How do you find PC, TC, and VC?
But those are the inflection points are safer.
Yeah, so PC, TC, and VC are characterized by when exactly. So actually, it's good that you asked this, and it's good, Patrick, that you reminded me. Very good. Yeah, I could not have avoided it. So great. So let's go back to, so let's write here. Thanks, Kinjal and Patrick. Now it's recorded in, for, huh? Nah. Umar already has shown up. His face is there, see? No, let's not get him too full of himself. Yeah, you forgot the glasses?
Yeah, I think it is.
Oh no. It's very realistic. So exactly. So how do we characterize this point? So going back to Kinjal's question, why did I say that this is where the phase appears? So if you look at this point, if you think about the slope of this curve, like slope was 0, then slope increase, and this is where the slope again starts to go down, right? But the same thing is happening on the left side also. So when you think about what is the point that mathematically what characterizes an inflection point? An inflection point is characterized by partial P by partial V at constant T is equal to 0. At the same time, partial square P by partial V square by T is equal to 0. So we want to solve for 3 things. We want to solve for PC, VC, and TC. This gives us 2 equations. Where is the third one? Equation of state. So we have 3 equations and 3 variables, right?
So this is for any inflection point would satisfy this, right? Not just
No, only this one. Because we have also said the slope is equal to 0.
So
Any inflection point would satisfy this one.
yeah, correct.
But we, on top of that, we are adding slope is equal to 0.
So anything
more.
that satisfies this is the critical part.
Anything that satisfies this plus equation of state is three equations, three variables. So it can be only three numbers, PC, VC, and TC. You won't have a surface, you won't have a curve. That is my inflection point, top of the dome. Go ahead, Patrick.
Okay, can you go back like one slide?
Mhm.
So, okay, so there, L plus G, the coexistence region, is different from L plus G in the,
In the Van der Waals.
go to the last slide, is different from those. Those are half of the original one.
Yeah, so here, if I had to be really accurate, I will draw it like this. This is accurate. That's how it connects to the real one.
No, it doesn't, because that has those have a bulge to the right.
No, it does.
Okay.
Oh, I see what you're coming from. This one. Yeah, you're correct.
Yeah, we didn't get rid of the second.
You are correct. We have to connect it over. Yeah. So the bulge should, you're absolutely correct. Let me redraw this. The bulge, good catch. The bulge should be coming from here. Better now? Let me redraw this, okay? Redraw on next page. This was, it will be the same curve, I'll just draw it clearly. So we have pressure, we have volume, and we find our inflection point. The inflection point still matters, okay? So it simplifies things in a sense. We find our inflection point, we go to the left, we go to the right, okay? That's what gives Kingel's boundaries, okay? We do this. At another one, we find our inflection point, we go to the left, we go to the right, okay? And now you can see how the bulge is starting to appear. Okay. At the very highest temperature, just beyond the top of this one, it will look something like this. So in this curve now, everything inside the blue is liquid plus gas. Everything to the left is liquid. Everything to the right is gas. Okay, and at this point, beyond this point, liquid and gas are kind of indistinguishable. They both coexist, they have the same density, there is no surface tension. They're just changing rapidly. And this is PC, VC, TC. Okay, good. Any more questions? So what we are seeing here is that the two-phase region of liquid plus gas gets smaller and smaller as T is increased. So this is high T, this is low T, and this is middle T. Until TC, after which surface tension between L and liquid and gas disappears and they kind of coexist almost. And we can find this mathematically by solving, first of all, so we can do it for any equation of state, okay? For Van der Waals gas, we would do P is equal to nRT by V minus NB minus an square by v square. Then we would do partial p by partial b at constant t is equal to 0. Then we would do partial square p by partial v square is equal to 0 at constant t. Once you solve this, you can actually get the answer. You will find that critical volume is 3 multiplied by b, the size of your sphere in van der Waals gas. Critical pressure is equal to A divided by 27b square. And critical temperature is equal to 8A by 27br. It's just algebra to get this. And I don't expect you to remember these numbers at all, of course. But you know, the idea should be clear as to how did we get this. Any questions? Okay. I'll wait for a minute before I go to the next thing. So this was our critical point, and we are not going to do much more about critical point. We will revisit critical point in StatMech. We will look at it from a different perspective. We will see that 1D systems cannot have a critical point. For 1D system, the critical temperature is 0. You cannot have phase transitions in a 1D system and things like that. And we'll calculate critical point in 2D and 3D and all sorts of things and develop some understanding for it. But for now, this is where we will stop with our critical point. We will think more about phase boundaries quite a lot. You have a question, Jared?
Yeah, so I'm just want to make sure I'm understanding this right. Are you saying that all the IG curves of PC and DC are in a critical phase?
They are L plus V. Yeah, there is no boundary. It's like they're.
Is the only reason I'm kind of like, I'm thinking like take CO2 for example, right? At a certain above a certain pressure, you guys are in the supercritical phase, right?
Yeah.
But below that, you can still raise the temperature and still be regular gaseous CO2.
Yeah, but I have raised the temperature now high enough. That's the thing.
Okay.
It's an isotherm, right? It's an isotherm. That's what you have
No,
to
no,
do.
no. My point is, you could be at higher temperatures,
Mhm.
but below a certain pressure, and still have gaseous CO2, like below the critical pressure.
You are saying that you could be at a very high temperature. So one thing to keep in mind is it a single component system or a multi-component system? Let's go back to our phase diagram of water, for example, right? So we have P and T, we have something like this. So what we are talking about is this point over here. Huh? Yeah, sure.
So here, I pulled up a phase diagram for CO2.
Uh-huh.
If you look, the critical region, its boundary is a horizontal line. So below that pressure, what this is saying is it's still gaseous no matter how high you get the temperature.
Mhm. Yeah, so part of the problem is also coming because we are using the van der Waals equation of state to explain
Okay,
our
and
picture.
Wallace-
So that's also coming.
okay, got it.
So we also have to go to a real equation of state to start thinking what's really going on.
Right, well, thank
Yeah.
you.
No problem. Go ahead.
So the liquid gas phase above the critical temperature must be the same as the liquid plus gas phase for the phase transition rate. Otherwise you have a quadruple point, right? Like,
Yeah, it's one phase,
Yeah.
and that's what here. So it's like the phase diagram that Jared just showed me. Basically, he was showing that all of this to the right of this is one phase, and it's liquid plus gas mixed together. Go ahead.
Does it mean there are thermodynamic characteristics such as specific heat identical for gas and liquid in that region?
What happens to specific heat? That I need to think about.
I think if you have it, because it's, so I think the difference between the normal liquid plus gas phase and the liquid plus gas phase after the critical temperature is that before you really have two separate phases, but now it's only one phase.
Yeah.
Before the liquid plus gas, but it's really one phase.
It is one phase, that's it. Yeah.
Liquid and gas. It's one.
Unless you can jump between liquid and gas without adding more subtraction energy. This can be a question.
So you are saying that the specific heat capacity at the very high temperature should be the same for liquid and gas. But there is no liquid and gas. It's liquid plus gas.
There's just this
it looks like a fractal. You think it's a liquid, you go and look at it in the microscope, you find, well, there is gas inside that. And you think, okay, now it's all gas, and you look further and you see liquid inside it. It's really a fractal, so there is no liquid and no gas. It is like a fractal. So that's why the confusion is coming, because there are no two phases. It's one phase. It's a liquid plus gas phase. It's the supercritical phase. Okay. So this over here, this that I am drawing over here, this is a two-phase region. Okay. This is a two-phase region, while this is one supercritical phase. And Jared asked a very good question, is to be more rigorous about what happens to it in this phase diagram. So Jared, can you send me a message on Slack about this? Send me a direct message or general, wherever, and I want to think more carefully if I could explain what you pointed out to me using van der Waals. I want to go and think about it. Okay, good.
Wait, are you saying that the L plus G's are different above the super?
Yeah, it's one phase. It's L plus G phase.
But then if you draw the top isotherm, you'll get a quadruple point if they're different, right?
You won't, because why would you get a quadruple point?
Well,
There is no quadruple. There is only three. There is only liquid plus. There is no solid here. You have liquid phase, you have gas phase, and maybe you have liquid plus gas phase. Why is that a quadruple point? That's still a triple
well,
point.
if the supercritical L plus G is different from the
Yeah, still it is. It is. This is liquid. This is gas. This is L plus G. So where do you see the fourth one?
if you draw it like this, you draw the top isotherm, then you'll see that they.
No, but it is L, G, and L plus G. Why are you saying that this L plus G is different?
So it's not a.
It's liquid, gas, and a supercritical phase.
Okay.
This is liquid. This is liquid and gas. This is gas. Okay, it's funky, and this is supercritical liquid plus gas mixed together. So what you're drawing, I see your picture. You're saying liquid, liquid plus gas, gas, and supercriticals have for fourth. I'm saying that no, this liquid plus gas is already this liquid and this gas. Okay. Yeah, critical points can get fun. You can keep thinking about it more and more. I feel sorry for poor PChem students in 481 and others. Often professors start with critical point, or like McQuarrie's book starts about it very early on. And I don't think they really appreciate it. You know, in order to get here, we have to think a lot, right? It took us time to get here. We didn't really use free energies, but still. Okay, let's move on past critical point, except I have to answer Jared's question, which he will ask me on Slack. And now what I want to talk about is really mixing of things, okay? Mixtures. So we saw some, I called critical point also as a example of a mixture, because, you know, two things are mixed together and you're seeing funky things. And is your doubt clear now, JP?
Yeah.
Yeah, you can, okay. If not, then ask me in Slack again. So I want to talk about mixtures, which is like all of chemistry, right? Chemistry is really mixing things, and we want to be able to characterize mixtures. And so what I will talk about today, and I will set up the problem and we will start, and we will see how far we go today. So let's consider Na moles of some chemical A and B moles of some chemical B, both at temperature T and pressure P. Okay. So the question I'm asking you is, imagine that they are in a container with a boundary in between. Okay. You have Na here at temperature T and P, and you have Nb here of mole of B at temperature T and P. So the A, let's say, looks like, or today is election day, right? So I guess I should draw red and blue. This looks like red, and this looks like blue. Okay. And let's assume A and B both are ideal gases. So how do you really distinguish one ideal gas from another ideal gas? You could distinguish one van der Waals gas from another van der Waals gas by having different A values and B values, right? For ideal gas, the only way to distinguish it would be to tag them somehow, right? Maybe you have colored them somehow, you know. Now I remove the boundary. Let's remove the boundary in the middle of the container. What will happen physically? What will happen to the pressure? It will stay the same because in spite of the boundary, they were already in mechanical equilibrium. Pressure was the same. The temperature will stay the same, but they will mix, right? You will have something that looks like Republicans and Democrats living happily together. Huh? What? That's why it's called an ideal world. You know? Let's call this as our initial state, and let's call this our final state. We are doing everything at constant T and P, right? So we want to think about spontaneity. What is spontaneous here? Is G initial going to be smaller than G final? First of all, why do we use G? Because we are talking about constant temperature and pressure condition, right? So Gibbs free energy is the unit to think about. Which free energy will be smaller, initial or final? Final, because we intuitively expect, right? In an ideal world, they mix together. In a real world, they won't, right? Because the reds really hit the blue and the blue really hits the red and they could clump together, things like that. And we'll study all that. So I want to calculate the value of GF minus GI. I want to calculate GI minus GF or GF minus GI and show to you mathematically that it is always positive. Furthermore, I want to show to you that GI minus GF for ideal mixing is equal to SI minus SF, and that HI minus HF is actually equal to 0. The free energy of mixing of ideal gases is purely entropy driven. And you might say this is obvious, but it's actually very interesting, and all kinds of funky behavior can happen due to this in colloidal systems and things like that. Colloidal systems are one of the best real world examples of ideal behavior. You have rods which are just moving around and don't talk to each other, right? Except when every once in a while they hit each other, right? And you can see these things in colloids. But let's try to prove this, that GI is more than GF, and you will actually derive expression. So we are starting with ideal mixtures, okay? How should we proceed? And the hint comes from the equation you all showed for me earlier today, mu is equal to mu naught plus RT ln P by P naught. That's what we are going to use. So I want people to help me write down the value for GI. What is the initial Gibbs free energy? It will come from Na moles multiplied by mu A, correct? Because Gibbs free energy per mole is mu, and it's ideal, plus Nb multiplied by mu B, right? We can write down mu A as Na multiplied by mu A naught, some reference chemical potential, plus RT ln P, right? And we are setting P naught is equal to 1 bar for both of them, okay? Plus NB mu B naught plus RT ln P, okay? Set P naught is equal to 1 bar. Everyone happy with this? This is a simple equation, but it can be confusing, especially if we did not do that mu is equal to mu naught plus RT ln P. You would be puzzled as to how did we get here. Any questions?
We're also assuming the phases are the same, right?
Well, right now I just assume, yeah, there is single phase. There's single phase. Multiple phases will come. I mean, it's an ideal gas, right? You saw ideal gas just doesn't do anything. It's boring, you know.
Because when you look at the mixture, I think at that point.
Oh, there will be lots of phases, but not in ideal gas. Ideal gas won't show you phases. It's really boring. But it leads to actually profound conclusions. I mean, I'll show you that in a moment. So this is my GI. Let me write it down on the next page, this equation once again. So GI, the initial Gibbs free energy is Na mu A naught plus RT ln P NB mu B naught plus RT ln P. And what is this equation number? It's a bit too late for numbering, but let's call it equation number 3. Now I need to think about GF. What's GF going to be? That's also going to be Na multiplied by some mu A, right? But it is now after mixing, plus Nb multiplied by some mu B. This mu A can still be mu A naught plus RT ln. We have to think about the pressure carefully. So let me draw the picture for you. So GF corresponds to, you have a box in which the blues are all now mixed with the reds. Who here got their undergrad in chemistry? A lot of you. Do you remember Dalton's law? Yes, that's your hint. So it's an ideal gas. So what pressure should I put here, Ethan?
So for
A.
we would have pressure of A over the delta. In this case, it would be Na over NB.
Let's go carefully. It should be pressure. It should be pressure, but it should really be the partial pressure. This is not using Dalton's law or anything like this. I'm just telling you that it's ideal. Just because you mixed it, it does not become non-ideal, right? It is still ideal. But now the pressure is not the pressure of the full container. The pressure is the container's pressure coming from A. Why does that make sense? Because what is pressure? Pressure is really your bombardment against the walls of the container, right? So A will be contributing to that pressure, B will be contributing to that pressure, right? And that's going to be PA and PB. This is actually quite generic. Dalton's law, which I don't remember, you expect you to remember the name, but for an ideal gas, PA is simply Na divided by Na plus Nb multiplied by P, okay? And PB is equal to Nb by Na plus Nb multiplied by P. This makes intuitive sense. For example, set Na is equal to 0. If there was no Na molecules at all, if it was only B, then what will be PB? That will be P, right? Nothing happened. What is another name for Na by Na plus Nb? Mole fraction. Does anyone here really like Shannon? Every time in this course, there is 1 or 2 people who are big fans of Claude Shannon. At least one person. Anyone else? So we will see why Shannon wrote his entropy the way he did. That's the answer. It comes today in this boring thermodynamics of mixtures. PB is equal to XB multiplied by P. Okay? So equation 4 can now be written as GF.
Yes.
Mhm.
That mu A naught is like I'm not able to. That's the chemical potential.
At some reference pressure.
Okay, so at your P naught.
Yeah.
Okay.
That's the same. It's just a value for A measured at some reference pressure. So that's not going to change because it's ideal. That's the thing. It's the ideality that is making this difference. And we will have a very systematic way of going from here to non-ideal behavior. But for now, it's ideal. So I don't have, it's a good point. So this mu A naught is the same, initial or final. It's just the reference chemical potential of A at some pressure. Okay. Partial pressure has decreased, but otherwise A is oblivious to B. It doesn't care. So Republicans and Democrats have mixed, but only at the cost of ignoring each other. Like, I don't think you exist. I'm just going to, that's the type of picture, the ideal behavior.
So when P is equal to P naught, I have the mu values, mu A naught, mu B naught. But then in the case of the mixture,
It's exactly the same. Mu A naught is the chemical potential of A when P is equal to P naught.
right, so, but that means you need both A and B.
No, you
components
don't.
To be exerting the same pressure, right?
No, you don't. Why are you thinking that? You don't. You really don't. You really don't. They are completely oblivious of each other. All you are saying is that the pressure experienced by A in this circumstance is proportional to the total pressure with the mole fraction. That's the only thing, okay? Apart from that, it's really the same. So think about the structure of equation 4 and equation 3. They are really identical, except that pressure has been replaced by partial pressure because you are now sitting in a container together. Okay, that's the only thing. Applies only for ideal, but it's so powerful, this framework, that it leads to more things. So GF is equal to NA mu A naught plus RT ln ln XA multiplied by P, right? NB mu B naught plus RT ln XB multiplied by P. So now we are ready to calculate our GF minus GI. This is equation 5. Equation 5 minus equation 3. Right hand side is GF. No, sorry, left hand side is GF, and here left hand side is GI. So GF minus GI. NA mu naught cancel out, right? NB mu naught cancel out. So what are we left with? NA RT ln XAP plus NB RT ln XBP minus NA RT ln P minus NB RT ln P. These two we can combine because the coefficient is the same, Na, right? So this becomes Na RT ln, and what is XAP divided by P? That's just XA. RT ln XA plus NB RT ln XB. This is the free energy of mixing for the total system. We are interested in the free energy of mixing per mole. Okay, those who are copying, I will write this down again on the next page, so you can just copy that. So GF minus GI is equal to NA RT ln XA plus NB RT ln XB. Okay, and let's call this as equation number 6. This is total free energy of mixing. Now we are interested in free energy of mixing per mole. So what should we divide this by? Na plus NB. So GF minus GI per mole is equal to, and let's call this delta mixing of G. Okay, and I'm not, whenever I write delta mixing, I assume it's per mole. Okay, some books use a bar to notate that it is per mole. I'm just going to talk about per mole. So delta mixing of G is Na by Na plus Nb multiplied by RT ln XA plus Nb by Na plus Nb RT ln XB. What is Na by Na plus Nb? That's XA. This is GF minus GI. we claim that they will mix. Their ideal, the free energy of mixing should be negative, right? GF should be smaller than GI. So this thing should be negative. Is it negative? XA is always positive, but XA is between 0 and 1, right? So 0 less than XA less than 1, 0 less than XP less than 1. Therefore, delta mixing G is negative. Let's try to plot this thing. And as I plot this, you're witnessing a very historic moment in my life. I think it was second year undergrad in one of my courses, and the professor plotted this. And I think this was one of the moments where I was like, this stuff is really cool. I really like it, and I'm going to do this. Yeah, it really inspired me. Maybe it will inspire you. I guess it's too late for you anyway. You're in PhD. Let's plot this. So I am plotting delta mixing G as X goes from 0, X goes to 1. And I know it's always negative, okay? So that's why I started my 0 up here. So it's always going to be negative. But my question for you is, how will it look like? What happens to it as X tends to 0? What is the value of delta mixing G? Also, by the way, let's do one thing. Let's call this as X ln X plus 1 minus X ln 1 minus X. We are talking about a two-component system where X is equal to XA.
There's also an RT.
Sure.
divided by-
You're doing physical chemistry. You're almost physicists. Units of RT. You're correct. I got carried away. In physics, we often care about units of KT, so we just ignore it. So can someone plot me for this? The starting point is, what is the value of this thing at X is equal to 0? Go ahead. Why?
Because if you don't, it's.
Oh, be mathematical. 0 log 0.
Zero.
Why?
The linear part is dominating over the logarithm part.
There is a rule for name for that in calculus.
Depends on-
Yeah, he speaks French. I always used to call it L'Hospital's rule. So it's L'Hospital's rule. Okay, L'Hospital's rule said that X ln X tends to 0 as X tends to 0. At the other side, it's obvious, right? Because ln of X is ln of 1 is 0, right? And as X tends to 1. So we as X tends to 1. So at both hands, this is going to be here. Now comes the fun part. So it's going to drop down in the middle. How quickly will it drop down? What is the slope of this thing? Let's calculate that. So we have X ln X plus 1 minus X. I will start from this curve last time because it is so important. You will find that the slope is actually minus infinity at both ends. It drops down to 0, to negative values, but with a slope that looks like this. This is how this curve looks like. And the interesting thing is, even though we did this for ideal behavior, this property that the free energy of mixing drops down with an infinite slope is actually true for almost everything. So it's very easy to add some impurities to something, right? It's always okay to add a little bit of impurities. For real materials, what will happen is that, and we will look at a lot of curves of real materials, this curve can look something like this. It can have all sorts of funky behavior. But at the end points, it will always be 0, and it will always drop with a slope of infinity. Go ahead.
The positive part for real material means they don't mix.
Oh, we will see a lot of reasons for the positive part, don't worry. Positive part comes from the energy of interaction.
While water and
You're going to spend so much time on it, don't worry, take my word. There will be a lot of time over the positive part where it comes from. We will talk about spinal decompositions and phase separation and all this beautiful stuff. Go ahead.
I'm good.
You're good. Very good. Okay, good. So this behavior, this minus infinity has profound physical significance. This means that creating a little bit of mixing is like hugely favorable. If you can have some defects, they will come and they will show up. And that's why, it's very it's difficult to create something which is like more than parts per million pure, right? You will always have that type of defect. The final thing I want to talk about, and so next time I will start from here, okay? And if I start from beyond this, remind me to start from here. I will most likely remember. I will start from this page. I will show to you that the slope is actually minus infinity. We'll work through this. And then next time I will prove to you that this delta mixing G is actually equal to minus T delta mixing S, that delta mixing H is equal to 0. So this process that we saw is purely entropy driven. It's only the entropy which is causing you to do this. There is no energy of interaction. So I want you to go and think about this. I will do this in class next time, how to prove this. Okay, how to prove this. We derived it for delta mixing G. We did not derive it for entropy of mixing. And when you do that, that's where Shannon got his inspiration, I think, because Shannon's entropy looks just like this. Instead of x log x, you have things like look at probability multiplied by log of probability. And that is the basis of information theory. It started around 1940s, which really was inspired by this formulation. So I want you to go and think about this. And next time we will start from, I will write down the expression for GF minus GI. I will draw this curve for you. And this is our ideal mixing. And we'll start from here, and then we will make it complicated. The next step will be to talk about regular mixing. Regular mixing assumes that the entropy of mixing is the same as ideal, but there is an enthalpy of mixing. And the people who looked at enthalpy regular model, we will talk about something known as the Bragg-Williams model, which is named after Lawrence Bragg. Anyone knows what else is Lawrence Bragg famous for? He won the Nobel Prize, right? You know what was special about his Nobel Prize? With his father, or maybe he was the son. And he still continues with the youngest person to win the Nobel Prize. I think it was like age 26 or something like that. It's too late for almost all of us, definitely for me. So, and then we will go to real solutions. So we'll talk about these solutions, and then we will, yeah. So we are going to spend a lot of time talking about phase diagrams. I'm totally out of Callan now. But if you wanted me to do everything that was in a book, why were you coming to university anyway, right? I mean, this is all for the interaction. But if you really want to look up this material, Atkins talks about it, Physical Chemistry by Atkins. Okay, so Callan has some phase diagram, but this stuff is how thermodynamics becomes practical. So that's why we are doing all this. So try to think about how to prove this. How do we get delta mixing S is equal to minus this relation? And Jared, you're going to tell me something to do. Any questions? So I will post the solutions to the homeworks and to the midterm before the weekend. Okay, so look at it. Most likely by Monday. It will take me some time. So I will do it before Monday, and then Tuesday, next Tuesday. We are meeting Thursday. Thursday we will do new stuff, but next Tuesday will be purely discussion. Okay, so look at the homework, look at the problems, and then send me an email, send me a message like Monday night, which things you want me to discuss, and then Tuesday we will have a discussion on those topics. And then there will be the midterm. The final exam, I posted the date online. It's going to be 14th December. That's the testudo date. And the time is 8 a.m. I can't help it. It will be this room, 8 a.m. to 10 a.m. You can bring one cheat sheet, this size maximum. You can bring shorter also. And you can write double-sided, whatever you want to write.
Good birthday present.
That's the testudo time, because otherwise I will have to go find a classroom.
Can we find a class?
No, good luck. And any of you who have ADS requirements, I will write to you separately on how to arrange the exam and things like that.